$100. I really hope this works.
Is it live streaming?
It's starting, so I don't know what that means.
So it looks good then, huh?
Yeah. Oh, it's on. It's on.
Oh, okay, cool.
Yeah. So, and then I don't know how to switch it to front camera. How do you do that? Oh, here we go. It's the top right here.
Yeah.
So it's the top right here.
Oh.
See that?
Yeah, I see it.
This tiny little one.
Yeah.
And this is all the YouTube stuff.
Okay.
So.
Cool.
Yeah. If you want to just
you don't want to use up your bandwidth, huh?
Huh?
Yeah, you can turn it off. You don't want to use up your bandwidth.
No, I have like a couple gigabytes, so it's alright.
Okay. Well, so you want to ask me any questions or something?
Yeah, sure. Okay, we're streaming, by the way. So I'm gonna go ahead and, yeah. So I need to make sure though, is the stream okay, you know? Oh, how do I...
Are you gonna put it on the tripod or?
Yeah, can you do that?
What?
Can you try doing it?
Can you?
Yeah, sorry, let me... You hold this, sorry.
Yeah.
It's on. Okay, you can just look at the camera.
Okay. So you like, you think it works better like that? Okay, there we go. So hopefully this is less choppy.
Yeah, so I'm gonna log in on IRC right now.
Okay.
I have all my logs and stuff.
And you can.
And then I'll ask people if the stream is okay.
So if you'd like to prop this up, snap that on.
Okay.
That's Kevin's, but
I actually use it a lot.
It's not. So you want to take it out of the case?
yeah.
Okay. I don't know how to do that, to be quite honest. Oh no, I can get this out. I have to unplug it. Oh, if I unplug it, it's gonna take the power out. If I have
You
to.
can plug it for a second.
Okay.
It looks like you still have a little bit of battery.
Oh, okay, so it's parallel. Okay. No.
I'm on 8. People have already posted the photo like online.
Okay.
So I'm gonna post a link to the live stream. I'm gonna ask people if.
So you gotta look at that. The camera's right there. Huh? Yeah, there we go.
Yeah.
Okay. So
yeah, let me. I'm gonna just get my questions out and.
is it looking a lot better, less choppy?
I'll make sure of that first. Actually, so
Yeah, for sure.
Shasta.
To Shasta. Wait, this is yours, right?
No, that's yours. You didn't finish yours, right?
I thought I did finish mine.
Oh, okay, so you poured it for me. Oh yeah, I wanted to ask you. Wait,
Hold on.
I gotta verify.
I actually used to drink Shasta a lot more.
700 people are watching.
Really? No kidding.
Is the choppiness fixed?
Well, it's on my bandwidth right now, so it could be fixed on the Wi-Fi.
Oh yeah.
Who knows, right? But the lowest it'll let you go is 480p, so that's kind of a problem. Oh no, it's not choppy.
Good.
Yeah, it's good.
It's good.
Awesome.
Well, I'm gonna check my data usage right now. Just to see how much it's taking, because we can keep streaming if it's not too bad. I don't want to like not have navigation back.
Yeah.
You know.
That's fine. I think we can get it on my phone. You just don't want to be overcharged.
You want to stop?
No.
Okay.
Okay, yeah, that's good. That's all right. Yeah.
So you
All
want
right.
to ask any questions or anything?
Yeah, so I'm kind of wondering what you think of macros, compile time macros. You know, like metaprogramming and all that stuff.
No. I like just define. Basically, to be quite honest, Gadwa was a big. He was against assembly macros, and you know how the philosophy. Well, here's the deal. I don't like. Introducing more things to look up to understand it. Like if you have to look, every time you have to change files to go look something up to understand it, it's with the low real estate system, the screen real estate, 640 by 480. Having multiple files jumping between them is especially painful. You know what I mean? So like if you have a macro, that's one more thing you have to go look up. That's not the reason for that. I just don't like macros. They changed the syntax in a weird way, and it could conceal stuff. It's not clear.
Yeah.
People abuse it. They abuse it. They start. I don't like that. So the things I don't like, I put a stop to. You know what I mean?
Yeah. So are you thinking of C-type macros or like macros?
Define. Like pound define.
Yeah. So
where they do
like list macros, if you can recall from your classes. I don't know, but because there's differences.
Okay.
Because C macros are a lot like messier and just not powerful,
Yeah, well, then you got assembly macros. Gadwa was really against those. You've probably never even heard of those. In the early days, they used to have on a 6502, they in order to add a 4-byte add, they would have to use a macro and stuff because anyway, whatever. No, I don't know about list macros. Remind me. How about that?
Well, it's a way to basically change one Lisp expression, or whatever you want to call it, into another by it will at compile time resolve the list that you provide as the arguments into an expanded function. So that way you don't have to type language, So instead of defining a function,
is this just like the Lisp has very few features? Is this just like the main feature of Lisp, or is this an extended feature, or what?
This is what distinguishes Lisp from other languages.
That's what I'm saying. Lisp is a super simple language, and are you just talking about?
This is how you would define extensions to the language. This is how you would.
Here's my question. Is this just the fundamental? Is this just Lisp has basically like only like one type of command or something. Not quite, but like you're just talking about the basic one type of command. It's not like a a secondary kind of. It's not a very complicated language, as I recall.
It's more so it's for defining syntax. So that's how you define new languages. So let's say you have a procedure and you want to start creating like a domain specific language. Basically.
I thought that all of it emerged out of. I thought all this behavior emerged out of like a very elegant, simple Lisp. All this advanced, it just emerged out of just like a basic, just the standard length. That was all emergent, something like that. You know what I'm saying?
Yeah. So Lisp has what's called homoiconicity, where every Lisp object is, it's composable. Right, so I know. Every object is.
I know that people like to use it for differentiation, solving calculus, or something like that.
So you could define a calculus language within a Lisp using that.
Yeah.
Anyway, I just kind of I thought it'd be interesting to see your perspective.
I never got into it, but
So what do you think about?
You've heard of lots of silly parentheses, right?
Yeah. It's a joke.
Yeah.
What do you think about I really messaging you. Composition versus inheritance.
So I programmed in C++ for. Did you ever try SimStructure? That was the. Okay, well it's a Windows application.
Yeah.
Yeah. I did not want C++ class inheritance in my Holy C because I wanted it simpler. You know, I'm not saying there's anything wrong with it, but you know, some of these things people are a little bit too enamored of. They see something shiny, you know, and like they see something shiny and they just love it. You know what I mean? And some of these things are a little bit overrated. You have to keep yourself from being too attracted to the little shiny things, you know.
Okay. Yeah, keep it simple, stupid, right?
Yeah.
Yes, yeah. And with objects, your Holy See, it kind of has a different object system than most other. Would you say it's inspired by Pascal, or where do you?
I have classes like from I took a structure and I made it. Class is it's a little bit. It's not just a structure. It's got
public-private or no?
No, I don't like public-private. I wanted
public, right?
Yeah, I wanted everything public. Yeah, I wanted it. I like the abuse and the power of assembly. You know what I'm saying? Yeah. So basically, I made it a raw, powerful language with no policemen. You know, no constraints. You know what I mean? So you can. I tried to make it maximum. Do anything you want. No cops. You know. So.
Yeah, like the Lone Ranger.
Yeah. If you want to do it that way, go ahead.
No random checks at the airport.
Yeah. So public and private, no, I had no use for that.
So someone's asking you to explain, ask him about one instruction set architectures, and we kind of talked about earlier. If you want to repeat some of that.
No. He's not talking about that kind of silly Turing thing. He's talking about like a new instruction set. Yeah, I gave a lecture on my idea for an instruction set.
Yeah, so that stream just was not.
Okay, I can talk about that. So some CPUs, I used like a 14-bit CPU or something, and all the operations were 14-bit. Temple OS is 64-bit, and I had the idea of doing all ALU computations at the 64-bit size in order to simplify the instruction set, and then the only time you use the smaller sizes is when you load them into a register or store them out of a register. So it would be like a RISC thing where like you load it into a register, promote it to 64 bits. And do your ALU operations, the arithmetic logic at 64-bit scale. I know sometimes if you do a 16-bit divide or something, it's faster. Sometimes on some architectures, but like as far as I'm concerned, it's not worth messing with. Do it all at 64-bit size. Keep it simple. And now the x86 is a CISC. And as it turns out, my compiler started as a simple stack machine, and the easiest thing was doing little RISC instructions. And then over the years, I converted over to CISC as I added optimizations. I combined together. I put optimizers to combine together some of my little RISC instructions, and I was disappointed because I did a lot of work to make these optimizations, and they didn't really have a performance impact. What I figured out is the x86 CPUs have pipelining that break everything down into little RISC things and schedule them. And so after going through all that work to convert RISC to CISC, the CPU just breaks it right down into RISC and starts scheduling and pipelining. And so the funny thing is, I could have had a terrible code that was just RISC, and it would have run just the same, and I could have gotten rid of a lot of those optimizations. And you can take out a lot of my optimizations and put it back to RISC, and it would run just the same.
Did you run any benchmarks?
Yeah, I did. My benchmark was the compiling the kernel and compiler. That's what it was. Is maybe on the order of a second or something. You know. Anyway, so you know, sometimes here's the thing I like to talk about is when it comes to so here's what I don't like about GCC. Instead of teaching programmers, okay, so
do you want to move the cafe or
no? Let's see. Okay. Instead of they like to brag about their optimizations, but my philosophy is the C programming language translates very. The C programming language translates very cleanly into assembly. It was originally designed to be very obvious how the C went into assembly, and what they started doing is let's just say you have sub expressions, right? You got an array lookup, and like for some reason you keep repeating the same array lookup. Well, they make the effort to recognize a repeated thing in the compiler. I don't. If you're a programmer, all you have to do is make a pointer to the. Let's say you got a couple dimensions array and then a class object or something, and you want to optimize the multiplies or something on the array indexing or whatever. So on an optimizing compiler, they recognize the sub expressions that are repeated, and they save some. But as far as I'm concerned, I like to keep it. I like it just a very simple translation of the C to assembly, and like if you want to optimize sub expressions, why don't you just go ahead and put a you're able to put a pointer in there and do it. And I like the transparency. Sometimes they go to sometimes I think there's a lot of arrogance for like optimizations that almost never happen, and you'd have to be really retarded to. Sometimes they optimize for idiots. It's like, why don't you just teach them how to program and don't make like these silly optimizations? Like I would imagine like you could probably get rid of half the optimizations, and they're probably for retarded programmers, and it's just arrogance. It's like, oh well, look at that, we can make an optimization in case you got this particular retard in there.
That's pretty funny.
So I like, okay, my philosophy is the C language translates very naturally into assembly, and mine is an unoptimizing compiler, and you know, if you you can pretty much do what you want if you just change the C to do it by hand, you know. Maybe not everything, but then you start talking about the particular CPU optimizations. I'm not talking about that. You know, the scheduling of the instructions. I didn't get into that. You know, if you really know the architecture, apparently you can start rearranging the instructions so that they intermesh and go into different pipes or whatever, all that stuff. I didn't get involved in that. One thing that's kind of nice is if you have a bad compiler, you can take joy in doing assembly. That's what it's kind of a funny excuse, but like in the old days, it was like, oh goody, I can optimize this in assembly. So I kind of like that. In the old days, you would take like the critical routine and then do it in do it in hand-coded assembly, and it's really hard to program in assembly these days. With in the old days you could, well, whatever, it sounded like an old man, but anyway.
No, I remember.
Like you used to be able to count the cycles, you know, this instruction's like 3 cycles, that one's 2 cycles, that one's 4, whatever.
Now it's all hidden.
Yeah, you can't even count it, yeah. It's all, the caching and all that is more important and stuff.
Yeah, can you talk about, you know, when you kind of like learned Big O notation at Ticketmaster? That's really interesting.
Yeah, we had a tutorial for like I don't know, maybe 4 months. Where basically they gave us like 10 tutorial projects. One of the most advanced one on there is the magic pairs under. It's on Temple OS in a demo. But yeah, we had to learn the you know, your basic sorts: heap sort, quick sort, you know, bubble sort, whatever, and the radix sort is one a lot of people. Do you know radix sort?
You've mentioned it.
See, okay, well, here's the fundamental. I've taken schooling, and the fundamental theory of sorting is comparison sorting is based on a game tree. You know, a game tree. You know, like a playoff in a basketball match or something, right? You got it's n log n is the limit that you can prove. You know. But that's for comparison-based sorting, where you have just two objects you compare. There's a whole new thing called, or a whole different thing called radix sorting, and what that is let's say you have an array of 256 element array of linked lists, and what you do is you take the let's say you have a bunch of strings. What you do is, instead of like comparing one to another, you just shove it into the list under that heading. I never really tried to implement it, but the point is, instead of just comparing two, it's kind of like you're getting 256 each chunk, or not really. You know how a case statement works, a switch statement?
Yeah.
Okay, well, you know, some people think it's just if then else, but it's not. Yeah, well, that's basically the difference between a radix sort and a comparison sort. Right? Yeah. So like that's the easy way to understand a radix sort is a comparison-based sort is like an if else. A radix sort is like a switch. So I took a numeric methods course, and we looked at there's Big O. Do you know what the flip side of Big O is when you're talking about numeric algorithm convergence? You talk about quadratic convergence. Let's say you have a Newton's method or something. You're trying to find a root or something like that. There's Big O is getting bigger, and when you're trying to find errors, it's basically the same concept, but you're zooming in on roots. You know what I mean? And just talk about quadratic convergence and so forth like that. That's like you know, you can do a binary search to try and find a root of a polynomial. But then, like, Newton's method is like a higher order convergence. And this is an example of the same concept as Big O. Anyway, you got Taylor series and so forth. Did you take calculus?
I did. I studied it, but
okay.
You know, I exited high school early because I decided to just program every day.
Okay, well, that's what Gadwa wanted me to drop out of school and go to work for Ticketmaster. The two of us started together, and the other guy dropped out of school and went into Ticketmaster, and he was there as a manager and stuff for, you know, a lot of years later. But so he didn't have any drawback. I don't know if he could have changed companies, but he was doing real good, you know.
Yeah.
So so Big O, yeah. It's just basically the when you have you round off to the major exponent. You know what I'm saying? That's more or less the way I look at it. So the other terms are less significant. Like if one term dominates, that kind of thing. So I haven't done a lot of. You're supposed to be able to look at a problem and decide what's the Big O of this problem. Yeah, and like when you're looking, I haven't done a lot of that. Here, what I do is like data sheets. Like you know, if you're applying at Google, they're gonna ask about Big O. But like what I studied was like, do you know what a data sheet is? If you looked at an architectural manual on like flip flops and like ports and like. Let's say you got a serial port. It's a hardware interface. You know what I mean? It's a.
And so each signal.
Here's what it has. Let's say you want. Let's say you want a 300 baud or 1200 baud is the old term for bandwidth, the old measure of bits per second, you know. Basically you had all these, you had to know binary, and you had to be able to read a data sheet and reset the hardware and control just bits and bytes and stuff. But like that's what I studied, is like data sheets, and what it is like for writing drivers, you know. And it's not really a lot of big O stuff, you know.
Yeah, obviously, because it's.
But what I did get into was, it was half hardware, half software. So we got into digital design, and I'm an electrical engineer, and I've done a little bit of digital design. Yeah. We learned how to whatever. When I was in school, you had the CPU was separate from the RAM, and you had to do glue logic to connect the CPU to the RAM and to the you had hardware ports. All that's integrated onto one chip now, or like you have an I/O chip now. But before it was all separate, and you had to like glue it all together. And so that's what I studied, you know. So like, reading. Yeah, I can say you can take your big O or whatever. I know the concepts. I just haven't really had a lot of opportunity to worry about it. I know they. That's kind of, the bread and butter of your programming job is not going to be big O. That's going to be once a year or something. Maybe you get you're worried about the big O, but like. What profiling? I took a supercomputing course. You know how to use a profiler?
A little bit, yeah.
That's the most important thing for optimizing. You get a code profiler.
And record like the stack and stuff.
I don't even think that
some profilers now, they have like you can replay.
Yeah. So maybe it's too complicated, but it used to be real simple. You just have a sampling of of what code it's executing. And then like you just draw a picture of where your hotspots are in your code to tell where your time is being spent. And then what you do is you just you say, okay, well this routine is using up all my time, so that's the one I'm going to optimize. Or you try to restructure it, you know. So like that's what you can have your big O, but like profiling is more important, you know. That's not entirely true, but
well, yeah, no, I get what you mean though. Yeah, because you're not working really on paper, right?
Yeah, basically you got the bread and butter stuff of what you do day in and day out, and then you got once a year maybe you're starting a new project and you get to do the high level big O planning or whatever. But like most of your stuff is not going to be the big O.
I'm really gonna use the toilet.
Okay.
I mean, you're still streaming, so if you'd like to say anything to the community, we've got a stream here.
Okay. So I had a plan for the architecture. So it's going to be a risk. So I had a plan for my compiler started as a stack machine, and what I did is I did basically reverse Polish. Instead of making a abstract symbol tree, you know how abstract symbol tree, you know what that is, right? So that's what every other compiler does. But I said, why don't I just put it straight into a stack machine reverse Polish, right? So I don't have an abstract symbol tree, so mine just puts it right in order, coming off the so like the optimizers and the code conversion on a normal compiler is done on an abstract symbol tree, but on my compiler I do it on a it started as an array of stack machine instructions, and I would optimize them, and I would eliminate some, and but I couldn't really add any. Eventually I put I converted to a linked list, the circular queue instead of the array, and so it started as a stack machine with really simple instructions. It was amazing how simple my compiler was at first, and I had an idea for a CPU where basically it's you have three different data modes. Assigned integer, unsigned integer, and float. And I don't like having. I like having just 64-bit float, like just to keep it simple. Like if we're making a brand new architecture.
JavaScript. JavaScript runs the web and stuff. All the web apps. They don't have ints.
Yeah, that's what I was going to tell you that on when I was doing my there was a point where I converted everything to I-64, and the reason was I looked at my code and I said, oh my god, I got all this inconsistency on my integer sizes and stuff, and I said, you know what I'm going to do? I'm just gonna do a global replace and put everything to I-64 because like the basic on a high level language like basic, like you could call it high level, it only had one integer, you know, like basic, basic only had one integer. Or some languages only have one integer size. Right. So I gave myself an excuse. What the heck? Let's call it a high level language. Do everything I-64, and so I didn't. So I made a rule. It's kind of you'll see stuff in there where it really shouldn't be the size I-64, but like my rule is use I-64 unless it literally breaks if you don't. It's kind of crazy. Like I've used the sign and unsign a little bit in some crazy places.
If you're doing a protocol with a fixed size buffer, you might want to have an int that's smaller.
This is apart from objects that are size significant.
Yeah.
If it's a significant size, then you want smaller ones. But like when it comes to like variables on the stack and stuff, you only do like 64-bit. So that's another weird thing. Well, you can see that in the Holy See. If you declare a byte variable, it's going to put it in a 64-bit and do operations at 64-bit because the compiler promotes everything to 64-bit, and it does intermediate operations at a 64-bit level. So like, if you take 2 bytes and multiply them, it's going to do the operation at 64-bit and then put them back. So it's strange, but that's the behavior I want because it's simpler. And anyways, I was planning ahead for an architecture where I was going to only have 64-bit ALU, and so I had this crazy idea for this cool architecture. What if you had a flag for signed operation, unsigned operation, or float? And then you had like 16 ALU instructions like add, multiply, and then like if your CPU mode is a float, then it does a float add. If your CPU mode is an integer, it does an integer add. So in theory you stay in the same mode, but in reality you're always switching. It's probably not so good, but
that wouldn't be a context switch, would it?
No. It's just assembly instruction like CLD. Have you ever heard of clear direction or clear carry or clear? Okay, so you could have a set float mode, and then the next instruction would be a float operation. You could have a set like if you stayed in the same mode, it would work pretty good, but I think you'd be switching a lot between them. I didn't investigate it. When they have these ideas, they test them out in simulators before they make a chip, to see if it's actually
good. Does this make you want to program right now? A little bit?
Well, anyway, so I gave a really good lecture earlier that got cut off.
Did you recite most of it, you think?
Yeah, these are all ideas I've repeated over and over.
Okay. Yeah, the comments aren't so good, unfortunately.
Comments aren't so good?
Mostly people memeing, you know what memes are, right?
Yeah, I guess so.
Yeah, they're just like...
They consider you a meme.
Oh, okay.
Yeah.
But,
They're like, can't unleash the wrath of God in this environment. Something like that.
So, my the CPU I want made is just going to be a real simple. I want it simple, like simple and clean. Like the x86 is that was one of the things I was saying. When you make it future proof, then usually that means the IBM PC was made not knowing the future, and now we know the future. Like they didn't know what a mouse is. Well, now we know a mouse is 2 buttons. Keep it simple. Now we know, so now's the time to like change everything to standardize it, right? At the beginning, they didn't know what it was going to be, and so they made it flexible. And right now, everything is clusterfucked because it's way too flexible. USB, I don't like USB because it's clusterfucked.
You were talking about that.
Yeah, so basically...
So how PCI is it PCI? Would it be like a modified form of PCI, or is PCI more complex too?
Okay, so I had an idea for if we were going to make an architecture friendly to Temple OS, what we would do is we would it's common for a hardware to have 2 modes of operation. A lot of the devices will work under the industry gets a new advanced mode, but it still supports the old mode. And my proposal was to you can go ahead and do all the standard PCI mode, but why don't you give an interface through the I/O ports to drive all the devices we use. So like right now there is a port. There's a port I/O for hard drives, and then there's a PCI mode, and that's just an example. That's already in place right now. But like it's possible that they don't no longer support the port I/O anymore. They could eliminate that, but we don't want them to do that. I want all this stuff done through I/O ports, not PCI, because there's a fundamental order of magnitude complexity. Just looking up the PCI is a big mess. Okay, so when it comes to simplicity, I want everything done with I/O ports. And I had an idea for mapping. You know, you have paging to add an indirection layer for memory.
Yeah.
I had an idea for I/O ports to add an indirection layer. So you just got a 64-bit or 65536 array, and that just remaps all the ports so that you can clean them up and make a nice structure. Just I don't know. And of course
that would be pretty high bandwidth too, right? It'd be high bandwidth. PCI is really high bandwidth. You know, that's why they use it.
I was just talking about a.
No, I mean for I/O devices. You know, it could support a lot of throughput, right?
Okay. There's on the x86 architecture. It's technically another bus called the I/O bus, or I/O. What do you do, an in instruction or an out instruction? This is a different bus from the PCI, which is done through memory I/O. The original architecture was designed to put all the in the original architecture, the memory operations were separate from the I/O. Okay, and then at one point the I/O no longer was sufficient to do anything, so they started doing everything on the memory. And so the modern PCI stuff is abusing. They're not even using the original architecture, and they're doing everything on the memory space.
Yeah.
And so
that's why the heap is so huge.
So they're not even using the I/O space. It's really it's garbage, you know. So it's like they're like no longer using the I/O space, and they're doing everything in the memory space, and it's just dismal. You know what I'm saying? So like one of the nice things about my plan for Temple OS is to do everything in the I/O space and keep it simple. Just looking up a PCI device is a nightmare because they got these class codes and stuff. And nobody obeys the standards. Like I tried to just go to a website and, well, what's the standard for this? It's like not standard, and you got to. Near as I can tell, you literally had to guess like 256 different IDs just to figure out which one it was because it was not standard. And I was doing these crazy searches. This is ridiculous. So I hate PCI. And another thing I don't like is USB because like they're like, oh well, what about the guy who's got 6 speakers on his sound system? Fuck you! Like you're gonna make all of us suffer just because this guy's got 6 speakers. You know what I'm saying? So they got these crazy, and then you get these crazy the HD audio. Like some of these things you have to configure. Like you got the HD audio. Let's say you got your headphones. You got your 6 speakers, and you got like a microphone, and just figuring out. Okay, let's just say I want to output to the speaker, right? It's a nightmare figuring out which one's the speaker, and like it's hard to. You have to route it through these crazy mixers and stuff in the HD audio, and it's like it took artificial intelligence just to figure out how to get it to the speaker. Do I really want to mess with it? I just want to write. So like, let's just keep this simple: 2 speakers on every system. a 2-button mouse. So if Terry was king, he'd fix all this clusterfuck. Like, go fuck you and your 6 speakers. Go like and buy a PCI card. If you want your flight simulator with 6 speakers, you don't make us suffer. You go buy a PCI card because we don't want to fuck with that. This is insanity. So I would simplify it down to like a standard system and eliminate, because that's really awful. They got these human interface reports in USB or human interface device. So like somebody's got like floor pedals on their flight simulator, and they got to waste all of our time with all that stuff.
This complex interface.
It's like, well, why is everybody else suffering? Because
like
this
million line long kernels.
Yeah.
Crazy.
Yeah.
Stuff. Yeah.
So oh well, you want to stop now? I'm gonna smoke a cigarette. How about that?
Yeah. Okay. Okay. We'll be back.
Where did I put him?
Maybe. We'll see.
Yeah. Oh, here it is.